So, to my amusement, the next question in Sierpinski's book is to prove that 13 divides 2 to the 70 plus 3 to the 70. I mean, this book was released in 1970. I'm firing up my computer algebra package. 2 to the 70 plus 3 to the 70 divided by 13 is apparently that number there. So, example, I claim that 13 divides 2 to the 70 plus 3 to the 70. Let's see if this works. Colon equals begin. End. So this isn't exists, this divide skull, so I'm going to use that. And then I'm going to go norm num. There you go. That's done that one. So I suspect that that is not the... why have I got an error? Unexpected in a comment block. I'm going to... Lean sometimes gets lost in comments. I'm going to restart Lean. There we go. Yeah, no warnings, no errors. I suspect that that's not the proof that Sierpinski wanted us to give. Because in 1970, kind of finding computers that could do that kind of calculation was probably a little bit more difficult. So what shall I do? Shall I think of another way of doing it? Well, I could do 13 divides 2 to the 7. So what are the powers of 2? So what are my thoughts? Powers of 2 mod 13. 2, 4, 8, 16. What's 32? Oh, 13 is 3, of course. Then 3, 6, 12. Aha, so we can't do any better than Fermat's little theorem, because 12 is minus 1. And then we keep doubling, we get minus 2, minus 4, minus 8, minus 3, minus 6. Then we get minus 1, which is 1. So 2 to the 12 is 1 mod 13, which we know from Fermat's little theorem. What about 3? 3, 9, 27. 27 is 1. So we can do a bit better with 3. I mean, what I'm suggesting is that we can actually... what am I suggesting? Let's have a go. Let's see if we can use Fermat's little theorem. Have we got? I think Lean's got Fermat's little theorem somewhere. Let's search for it. Fermat's little theorem. That's an IMO question. Oh, Fermat's theorem. That's got nothing to do with anything. That's got something to do with analysis. Fermat's little theorem. So let's have a look at this. So Fermat's last theorem. I don't think we're too bothered about that. Fermat's that theorem on sum of 2 squares. That's not relevant either. Fermat's primality test. So it looks like this is Fermat's little theorem. So let's see what we've got. It looks like there's 3 versions. So that one is a statement about Z mod P. That one's a statement about Z mod P. And that was a statement about congruent to 1 mod Z mod P. So we had quite a lot of success using Z mod 13. Let's try Z mod 13. So example, let's try and prove the same theorem again, but in a way that Sierpinski would be more happy with. Begin, end. Now what was that theorem called? I'll probably just look, can't I? This thing here, Z mod nat coi blah blah divot. So I could rewrite this. To import it. What was the import called? Data.zmod.basic. Is it this way? Yeah. Great. So now I've got to prove this. And now I wonder if I can push neg. Oh, I can't do that. Not push neg, push cast. And I can do that. So change 2 to the 70 to Z mod 19. I don't know why it's taking it apart. To the 70 plus 3 Z mod 19 to the 70 equals 0. Oh, Let's try Z mod 13. Might have more luck. Yeah, that's worked. Right, and now, what does Fermat's little theorem say? It says a to the p minus 1. So which one are we going to use? Let's use this one. Power card sub 1ec1. That looks like the best one, doesn't it? Have h colon equals this. That's not a thing. Oh, it's not a thing. I have to import it. What's it called? SRC Field Theory Finite Basic. Import field theory dot finite dot basic. Oh, it's still not a thing. But oh, interesting. There is actually 4 of them. We can see what they say. That's the modec one. Aha, that's the general finite field one. I think this is the one that will this will do for us. So it would be nice to prove that that 2 to the power 12 is 1, right? I mean, that surely is going to help. So have h1, 2 in Z mod 13 to the power 12 is 1. And I'm going to do that by applying this theorem. Which will hopefully be applicable. No, it wasn't applicable, hard luck. It's failed to synthesize. Right, so apparently we need to tell it that 13 is prime. What does it want to do? It wants it as a fact that 13 is prime. So I have h0, I claim that nat.prime 13. And I think normnum does these. It does. But apparently we need this statement, we need this. You see, if I hover over this, do you see that we've got a square bracket? I'm going to prove nat.prime p, but it's in square brackets, which means the type class inference system needs to know about it. So I'm going to do have I fact nat.prime 13. And that's going to be, I've forgotten what it's called. There's a way of, that'll do. I could probably even do, I see, to make a fact you just have to give a, this will probably work. Yes, and now the apply works, great. And now I've just got to prove that 2 isn't 0. Will normnum do that? Will normnum do that? No, apparently it won't. How am I going to prove that 2 isn't 0, I wonder? You see that all you've got to turn it into a question. This is it seems to me that we've been using divisibility and that's been working fine. But now sometimes it's just easier to work in the finite fields. And then you see we lose a whole bunch of tactics. Right, I mean, in the finite field with 2 elements, 2 is equal to 0, so we have to be a bit careful here. So why don't we rewrite this thing again? This seems like a useful thing. Rewrite this. Oops. Oh, hard luck. So intro h2, and then I could rewrite this thing as h2. Apparently I can't write this thing at h2. Oh, what a bore. So, okay, let's press on then. 2, the natural number 2, when I reduce it, Z mod 13. I wonder if I claim that thing equals 0, and the proof of that is assumption modcast, right? Because yes, it is. And so now I can rewrite this at h3 probably, all to prove that 2 isn't 0. And now I've got to prove that 13 divides 2, and so now I can revert h3, and now norm num will work. There. So, oh, that's slow. That is slow. I don't want to be, if I'm just gonna comment that out, put sorry. And now that's much quicker. So we'll uncomment that at the end. We want to get everything compiling. Yeah, we could have just proved that 2 to the 12 is 1 by brute force calculation, couldn't we? So, do you know, like, why don't we have h2, I claim that 3 z mod 13 to the power 3 is 1. And that, can I do that by refl? You see, that's quick. Yeah, there's no point. I mean, Fermat would give you a weaker result anyway, but tell you that 3 to the 12 is 1. So now what I'm hoping is I can use these facts to actually work out what 2 to the 70 and 3 to the 70 are. So let's rewrite, show 70 equals what? 70 equals 12 times 5 plus 10 by, I don't know, by norm num. Does that work? Yeah, that's kind of interesting. Oh, it's kind of, I only wanted it to rewrite the first one. Well, while we're here, I'll show you conv mode. Look at this. Conv begin, end. Conv mode is really cool. Let's see if I can work it. So conv mode, now we don't have you can tell we're in a different mode now. We're not in tactic mode anymore now. We're in some crazy mode. We're in conv mode. And then we can do conv LHS even. It'll save us the first step. And you see, these aren't propositions anymore. These are just terms. So it's a way of. And now what do I do if I do congra or something? Isn't that? I've forgotten how. Bingo. And there we go. And now we've got 2 to the 70 and 3 to the 70. And then I want to do this. Now, can I do that? I wonder. Is that a bit clever? Oh, that has worked. Excellent. And then I'll skip this. And now I'm going to rewrite. Show 70 is, what do I need? I've got 3 to the 3 is 1. So 70 is 3 to the power 23 plus 1 by norm num. And great. So there we go. And now let's rewrite power add. And let's rewrite power add again. And now let's rewrite power mul. I suppose, is it called power mul? It is. Great. Power mul. There we are. And now I've got a 2 to the 12, so I can rewrite h1. And now I've got a 3 cubed, so I can rewrite h2. And now let's try simping it. So now the question is, so 2 to the 10 is 1024. Did Sierpinski know that? And I add 3 and I get 1027. And so can I prove that 1027 is a multiple of 13 without using a computer? And 1020, I could just do it by 13. Is it true? 13 fours are 52. 13 sevens are 91. 1027. I got it. 1027 is a multiple of 13, because if I add 13, I get 1040, which is 10 times 104, and 104 is twice 52, and 52 is the number of cards in a pack. And that's 4 times 13. So that's a proof that 1027 is a multiple of 13 that I can do in my head. So I'll allow myself to do refl. There we go. And I reckon that's a proof that Sierpinski would have been happy with. And so that's the end of this video.